So I'm going to start with an introduction about colour and using colour as a diagnostic tool. And then we're going to look at individual body types associated with the colour one at a time. So this is a seminar run by our company called Epigenetics, and you may be familiar with the word epigenetics. When we first formulated the word in the company some 3+ years ago, it was a bit of a word that nobody had heard about, and I think the team had difficulty in even pronouncing it. And then all of a sudden they started to, I heard that on the radio, on the news program about epigenetics, but still nobody really knew what it was about. So first of all I want to define what it is. So epi means above, okay? Like epidermis, which you've got on the skin, is the outer surface, so epi means above. So epigenetics means things outside of the gene that can affect it, particularly above. And we like to think about our influence epigenetically on people's gene expression by altering their diet, by supplementing them with particular nutrients, by detoxifying them of heavy metals and chemicals and radiation, and being able to treat them as far as energy deficiencies, which we'll be looking at briefly today, having a look at their diet in case there's anything that they're allergic to or sensitive to, improve their oxygenation, and lastly the effect of the emotions having the effect on the gene expression. So that's what epigenetics is about. So we know that genes are responsive to the signals of the environment. So the more toxic of the environment, if you've ever been to anywhere which is really toxic in Asia and Russia, you'll notice one of the first things, apart from you'll have difficulty perhaps breathing and you'll get tired, is my experience, about how old the population look. And when you ask them how old they are, a 50-year-old will look 60 or 70 because of the effect of free radicals generated by the chemicals in the environment. Epigenetics is the control of gene activity by environmental signals, the mechanism by which we control our genes. And we'll be talking through the series a lot about how we get genes to express themselves, which we want, called suppressor genes in the case of malignancies, and how we keep the tops and stop other genes from expressing them by keeping methylation caps on. So the gene expression is all to do with acetyl groups to allow genes to come off, to express good genes in our genome mechanism, and methylation groups which keep the caps on genes which we don't want expressed, which maybe we've inherited from family, mum and dad, etc. So epigenetics is mediated by the environmental signals through also our perceptions of how we see the world. And we'll be looking at that today because people who go under emotional stress for a period of time change their physiology and their metabolism. So we all know that if you've been under a lot of stress, some people gain weight and some people lose weight. It's a fantastic way of losing weight, but on the other hand, if you're under stress and you gain weight, it's not a good thing. Okay? So we'll be looking at the way that perception can change how we see the world, how we react to the world, how that can alter our chemistry through the hormonal system. Therefore, misperception, if we think we're under stress or we've got the idea that we're being under particular types of stress, which we'll have a look at, misperception can also misrun our genes. So we can run programs in our consciousness, or rather our subconscious, which referred to things way back in the past, and they may not always be the truth. So one of the first things we used to teach at the British School of Osteopathy, where I used to teach nutrition, dietetics, and then anatomy, functional anatomy, and we used to teach our first-year students who come straight from school or other careers, is that people are different shapes and sizes. And we all know this, and this is how I tell my patients, is some people are tall and some people are shorter. Don't be derogatory about it. Tall, shorter, and some people are in the middle. Okay? So we all agree there, but we've not got a definition of exactly their heights to say you're a tall person, a medium, or a short. So we'll go into what is generally a height for a tall, a medium, and a short person. We also notice that people are different structures. Some people are very muscular, and some people are more portly, and some people are very thin. Okay? So along with those different heights, we get different body builds as well. And we'll be looking during the morning and also body skeletal changes. Some people have very narrow rib cages, don't they? So they're very narrow here, and some people have very broad rib cages around here. And some people have, have very long fingers. Have you noticed that when I look at their fingers, they're very long, and some people have very short fingers, as if the top digits are missing. And some people just have big hands, like mine. Okay. So people are different shapes and sizes. And in years gone by, these were called ectomorphs, mesomorphs, and endomorphs. And we see here the ectomorph on the left there is the more thinner build of a person. The mesomorph is the more taller type of person, bigger build, usually fairly muscular, and the endomorph on the right is more of a shorter and more plump build usually. So on the male side, we see again the ectomorph, the thinner man, medium height. Then we see the mesomorph, who's the bigger muscular type of man, and then we see the more, the shorter, more rotund endomorph. Now we know that light affects us in different ways. We actually see light on the visible spectrum in a very, very short, narrow parameter of wavelength. So of all the wavelengths which light is measured in, as opposed to sound, which is measured in frequency. So on the left here we've got the octaves of sound, and on the right we've got wavelengths. Now the visible spectrum is between 380 nanometers, as it's referred to, and about 770. So we've got quite a small parameter, about 400 nanometers maximum of visible spectrum that we can see. When we go beyond the 380 in the violet end of the spectrum, we're going into ultraviolet. First of all into ultraviolet A, which is not so bad for us. Then we go into ultraviolet B, which can be toxic and also can be good. And then ultraviolet C, which is largely reduced by the ozone layer. And this is the danger: as the ozone layer begins to thin, we'll get more of the shorter wavelengths, which can penetrate much deeper through from ultraviolet C. Beyond that, you go into X-rays, and then eventually into cosmic waves and gamma waves, so the smaller the frequency, the smaller the wavelength. On the red end of the spectrum, when we get to the end of the red, we go into infrared. So we get soft infrared, or near infrared first of all, and then medium, and then distal. And the infrared is mainly heat. So in the infrared and the ultraviolet we don't see with the human eye. But it doesn't mean, of course, it's not there. Because you know, if you go out into the sunshine in the summer and take your clothes off, you will be exposed to both ends of the spectrum. So you feel hot, which is associated with the infrared, and you get a bit of a tan as you burn the skin from the ultraviolet. Okay? Now, ultraviolet is very necessary, particularly around the 280 to 300 nanometers, which is below what we can see, in order to penetrate through the skin 5 layers to convert cholesterol into vitamin D. So we know that light is therapeutic for us. It helps us to make vitamin D. And it probably makes 95% of the vitamin D levels and storage in the body is made from the sunshine through the skin. But of course it's only when the sunshine has that 290, 300 nanometers, which means it has to be above 45 degrees. When the sun is lower than 45 degrees and your shadow is longer than yourself, you're not getting ultraviolet at that level. So it's a simple way of measuring whether you're going to make ultraviolet or make vitamin D from the right level of ultraviolet is the length of your shadow. So if you stand in the midday sun and your shadow is shorter than yourself, take your top off for about 20 minutes, half an hour, and you will make vitamin D. Okay? If it's longer than yourself, don't waste time. You'll get a cold from that end. So ultraviolet, we know, has beneficial effects to us as well as harmful if you're in it too long. Another example of light would be at this time of the year, certainly at midday, our shadow would be very long. And we don't see so much of the violet end of the spectrum. Why? Because the sun doesn't come up high enough. Therefore, in what we call white light or daylight, is missing in the winter time a lot of the violet end of the spectrum. And it's the violet end of the spectrum which seems in the body to stimulate the production of serotonin. So serotonin is a chemical which we'll come across, a brain chemical or neuropeptide, which basically keeps us on a level. It doesn't give us a high. It's not like dopamine, which gives us a high. Serotonin keeps us on a level. So if we sink in our serotonin, we feel sad. And it's called the SAD syndrome. But another name for low serotonin is the blues. So the blues you think of associated not just with the music, but feeling sad, basically, which is what blues music was all about. The hardship in the north of America for the coloured workers there. So the blue end of the spectrum doesn't lift us up, but the violet does, all right? So at this time of the year, you get principally the blue in the sky and not the violet. That's why the sky looks different in the winter than it does in the summer. So even if you go out and it's nice bright light out there, it won't elevate your serotonin. And so they found that giving broad spectrum light in a light box was a very good way of elevating people's serotonin during the winter. Okay? But it works even better if you put the violet end of the spectrum on the light box and get the person to look at that for about 15 minutes. And this will really help lift their serotonin. So these were the first discoveries that light has good effects in the body as well as harmful. Now, some 15 to 20 years ago, I can't remember exactly now, I had two elderly ladies who came to see me in my clinic, and they were sisters, if I believe, or close friends, but they both had a condition called macular degeneration. And basically all they wanted to know was whether a product called lutein and zeaxanthin would be a benefit to them. And I'm fairly well experienced because I taught nutrition and things and anatomy for years. But I'd never heard of lutein and zeaxanthin, and I'd never really ever come across a case of macular degeneration. I think I'd heard the word, but I really knew nothing about it because that's not what people normally would come to see me about. So I tested them in the standard applied kinesiology way, from weakness basically, to see if the product strengthened. And as I remember, it did. So I became interested in it because lutein and zeaxanthin, the capsule mix was an orangey yellow colour. So I thought, if it's supposed to be something to do with the cones in the eye which pick up colour vision, and this is supposed to supply pigments to help protect those cones from the light, if I make a series of acetates through the spectrum, I should be able to test these two ladies to see which colour might be beneficial, and is the yellow and the orange beneficial to them? Or maybe a colour might also be detrimental. So what I did is I made 7 true colours. Okay, these are called monochromic colours because they correspond exactly to the nanometers of pure light from the red end of the spectrum to the violet. So I made a pure red, a pure orange, a pure yellow, pure green, pure blue, pure indigo, and pure violet. So the 7 colours of Newton through the prism, or the spectrum. And I was pleasantly surprised because I found that indeed the yellow-orange did strengthen these two ladies. And I was also quite surprised because the violet end of the spectrum weakened them. Okay, and I didn't understand anything about colour or the reason why that might be. But I knew that there was a thing called a pin wheel of colour where you have equal and opposites, if you like. And the opposite colour to yellow and to orange is the blue-violet end of the spectrum. Okay? So what happened with these two people is exposure to the violet end of the spectrum created a stress in them in some way which the orange and the yellow improved or negated that stress. Okay? So that's how my brain was thinking, sort of logically in the process. And then a close friend of mine in the print industry said, he said, there aren't really 7 colours. I know there's 7 colours distinct as they go through the prism and they go in different ways through the prism, different angles and things. But he said in artwork, there's only red, yellow and blue. And in optics or light, there's only red, green and blue. Okay? There's only really 3 colours. And what happens with those 3, most colours, or all colours, are either those one of each of those or blends of them. Okay? So we know that turquoise, for instance, is a blend of green and blue, isn't it? So it's a blend. So it is a pure colour. If you go from the spectrum from the red end right the way through to the violet, we see turquoise there. If you look at a rainbow, you'll actually see turquoise there. But we know there's other colours like brown, isn't there? And brown is a mixture of red and green and a bit of black in there. Okay? So many colours that we see in this room, and I'll have a look round, are not true monochromic colours. A true monochromic colour will be a precise wavelength to it, which you can measure and reproduce, and I reproduce these on the computer very, very accurately. So if I said 480, I could reproduce you exactly the colour of 480 in the blue zone. But if I look around and I look at Harris jersey is a brown colour, and you say, well, what is brown? You know, it's definitely got black in it. It's probably got a bit of red and a bit of green in there. And with a mixing of the palettes on the computer, I could probably make a match for Harris jersey there. So when you buy paint or you want anything to do with colour, you get what's called a swatch card, and it uses those three prime colours, the red, green and blue, and gives you proportions of them. So you'll see a graph which has a high degree of red in it and maybe a high degree of green, but only a little bit of blue. And when you mix all that together with a bit of black coming in, you get Harris jersey. Okay, so this is a trichromatic effect, in other words, three colours. Okay? Now we see in trichromate vision. So we see three colours, okay? And that's all we see. And the beauty of the human eye is each colour, red, green and blue, is offset from the true mid-range red, green and blue. So the cones, which are the receptors for the colours, the wavelengths in the back of our eye, we have three, red, green and blue. The red cone is offset towards the orange end of the spectrum. The green cone is offset towards the yellow end of the spectrum. And the blue cone is offset towards the violet end of the spectrum. And this allows us to see 5 million shades of colour. Okay. Whereas if we were only set to mid-range, red, green and blue, we would be like a colour television set, and there'd be certain colours which we'd be missing. For instance, a digital camera or colour television set does not see gold, and it doesn't see lovely crimson reds of a peony plant or many flowers. And you take a picture of a lovely peony plant and you print it off and it comes out red. And you think, oh, where's that lovely sort of darker red gone? And it comes out red. If you take a picture of gold and you print it off, it comes out yellow. So the computer and the camera see it, but they can't record it and put it into colour. The human eye can. So we can see things which the camera can't or can't reproduce. On the other hand, we also see a very, very narrow range of the spectrum, very, very small. If we could see into ultraviolet, things would look very different. They would look violet. They look more like Jane's top there, apparently. But we don't know because we can't see it. So don't think ultraviolet is like Jane's top. But people who can see into the ultraviolet and have experienced it have had short visions of this say that it's violet, a light coloured violet, certainly in the early range. And there are people who can see a little bit more into the ultraviolet than what I can and most of us. And this is after cataract operations. So after a cataract operation and they put a false lens in, that lens sometimes allows a little bit of the ultraviolet to come through, certainly for a month or two. And they say, I can see colours after my operation that I've never really seen before. I haven't seen them for years and probably never seen them before because they see into the ultraviolet side. This was evidenced by a research on a pilot who had I was reading a pilot who had a cataract operation, and he swore he could see violet where everybody else saw black. So as I go from the red through the spectrum to the violet end of the range, and my violet then disappears, it goes into black because I can't see it, so it has no colour. And so an absence of colour is black. But he was able to see black things as violet because he could see just that little bit far. And they weren't sure they believed him. So they got a monochromic device which put a beam of every 5 to 10 nanometers right the way from 200, which nobody could ever possibly see, right the way through to the visible spectrum. And he was right, he could see it. He could see it close to the visible spectrum in sort of 370, 360, and his world was different because he saw everything as being violet. Now imagine if you could see a few nanometers beyond 770 on the red end of the spectrum, you would see heat. Everything would be hot. You would actually see the response of heat. And some animals are like this. For instance, owls and most birds of prey see in the infrared zone much more than we do. And this is the misfortune of any mouse that happens to be on the ground, because a mouse may be running in the wheat, so that nobody can possibly see it, but a mouse every few seconds drops 1 drop of urine. Okay? Stupidly, it doesn't hold on till it gets to a toilet. It drops 1 drop of urine, which is spotted by the owl from a great height. Okay? And it sees these heat spots, and it gives itself away. So the bird of prey can come down and take it in the middle of the night, but he can see where that urine is and know that there's a mouse there. Okay? So wonderful world if we could see just a little bit more, wouldn't it? Fish, for instance, don't see anything in the red end at all. They see in the violet. So fish are able to, because the red end of the spectrum is filtered out by the water. Okay, so they only see much more into the violet end. So they're able to see ultraviolet much more than we are. So we only see what we're programmed to see. I don't even know whether I see the same as what you do. We don't know. I've been told, you know, your jersey is bluey red, but another person may say, oh no, that's got you know, more violet in it. And we get certain colours which are really quite difficult sometimes to define, and this is one of them. So this is definitely pink. But somebody may say, oh, that's a touch of magenta in there, a little bit of red in there, we know, and definitely white, because pink is red and white. But maybe there might be a bit of blue. If you put a bit of blue in there, we'd be moving over to the sort of purple magenta end of it. I wouldn't like to say there was no blue in that at all, but we know we don't see many girls wandering around with that hair. So pink is not a real colour. Okay, that's what I want you to understand. If we're going to measure colours, we've got to see how the human eye sees it. And the human eye sees it in 3 pure cones or receptors, red, green and blue. And we remember that they're slightly offset towards one end of the spectrum. Now, how can we put this into clinical practice? The answer is we make acetates or filters of precisely those wavelengths that the human eye is set to, each cone is set to. Now, they were 15, 20 years ago quite difficult to find. We found most of the information in books on photography rather than books on physiology. And I was able to calculate the wavelength accordingly. So the one which was well recorded was the 619 nanometers in the red end of the spectrum for the red cone. Now I was able to therefore calculate out, when I got the blue end of the spectrum, by drawing a line through, I could determine, and muscle testing, where the green one was. Okay? So I put figures of so many nanometers, 440 nanometers for the red, for the blue cone, 565 or 570 for the green, and 619 for the red. So we were happy with that, because what we found is, my friend was right, when you put either the red one on, or the green one, or the blue, people either strengthened or weakened. Okay, and what we found was amazing is that every single person weakens to one of those 3. Okay, so the question is, why do they weaken to one of those 3? And probably from a neurological point of view, what happens is we overstimulate the cone. For instance, if I put red on and a patient goes weak, in other words, it's a stress to them, we're putting too much of that wavelength into the cone, which is then overfiring. It's overstimulating through the optic chiasma to the thalamus, and hence from the thalamus to the hypothalamus, to the medullary reticular formation, the intermediate lateral cell columns, which is the motor supply down the spine, to the supraspinal gamma motor neurons, and then on muscle testing at the neuromuscular junction, we find we get a weakness. And generally speaking, in our functional biochemistry, kinesiology approach, anything that changes the body muscle power from its normal state of strength to weakness is detrimental. I think we probably all agree there, something that weakens us is not good. Conversely, something that brings us back from a state of weakness to the normality of strength is something which is good and therapeutic. So we could say that if a person weakens to the acetate, the red, green or blue, it's an overstimulation, okay? It's putting it in. Now the question is, why do they weaken with what is a normal colour, which is every day around us? And the answer is we don't have the protection in the back of the eye to that particular wavelength. But we know there's only 3 wavelengths that we see in, and everything is a blend of those 3 colours. Now what we discovered later on is there's a substance called melanopsin. Now the eye is 95% rods. And rods are basically particular cells which pick up dim vision, shades between dark and light. Some pick up outline, but melanopsin rods are particularly rich in this melanin substance, which picks up more shades of dark and light. When you study melanin, you know that there are 3 types of what are called eumelanin and pheomelanin altogether. And this melanin, in other locations of the body, determines our skin colour. So we know some people are dark, and some people are medium, and some people are light. And we know the same with hair. Some people have dark hair, some people have no colour at all. In other words, they're blonde or even white, albino there, and some are brown and some are dark brown. And this is all determined by the quantity of melanin. And this is entirely genetic. Entirely genetic. So the colour of your hair is entirely genetic. The colour of your skin is entirely genetic. If you have, if you're white and your parents were white, you're likely to have children that are white. And conversely, if you're black, you would have black children with a black mother and father and all the way through. So it's genetic. If you've got green eyes right the way through, you probably will end up with green-eyed children, and so on. So it is, the colours within us are genetic. So therefore, it would make sense that the melanin present in the back of the eye to protect against certain wavelengths is also genetic, which is why if you're a green person, what I call a green person, in other words, I weaken to the green colour, and I marry a green person, probably a good likelihood is most of our children would be green, or weaken to green. Okay, they would be their body types. So in other words, tall parents tend to have tall children. But occasionally they don't, do they? Occasionally you get a shorter one. And what we found is that sometimes a short person will weaken to blue, but not necessarily always. It didn't seem to sort of fit at that particular time. So in those days, and I'm talking 15 plus years ago, we just took it that people weaken to one of those colours. What we didn't know, there was a significance to that as far as their whole physiology and metabolism. And then I noticed a couple of friends who were patients who were very fit and health conscious. They were probably 10, 15 years older than myself, but we used to socialise quite a lot, and so we were quite close. And they were very health conscious. And this is, I'm talking about 15, 20 years ago. And they used to take antioxidants, A, C, and E. You hear about people who take antioxidants to protect them against free radicals and things, and this will inhibit the aging process and so on. And I hadn't really got into this that much at that particular time. But they'd taken them for years, and a bit of selenium, that was the other thing. Selenium ACE, it was called, the product, and they'd probably taken it 15, 20 years. And both of them started to get, or had got, digestive problems in different ways. And in those days, when I started doing applied kinesiology and muscle testing, I got great at determining what foods people could eat and what they couldn't. So you're allergic to so-and-so, you're allergic to this. So I would take people off all sorts of things. But I noticed these 2 friends are both weakened to wheat. So the answer was quite simple. I just took them off wheat, which is not as easy as you can imagine to eliminate wheat entirely. They weren't sensitive to rye and other gluten proteins, but it was strictly to wheat. So we had times when we took it off, and their guts improved. But interestingly, their health didn't, but their gut was a bit better. And as in the fullness of time, going on another 5 years from probably this period, firstly, the lady developed. All this time she told me she got memory problems, developing memory problems. And then about 5 years later, she was admitted to a hospice with Alzheimer's, so-called. And within a year, he was in the same hospice in another room, and because he didn't know her and she didn't know him. And they were in the same hospice. Didn't know who each other was. Isn't that amazing? Probably been married for 35 or 40 years. But I remember the track, you know, that these two were very healthy in every way, but they were of medium height, so they weren't tall and they weren't short, medium height, both of them. Both were highly sensitive to wheat, and both weakened to red. Okay? So don't worry, this doesn't mean that all people weakened to red are going to get Alzheimer's. On the other hand, most people get Alzheimer's do weaken to red, we found. Okay. So that was the first clue. This is interesting. I wonder if it's something to do with foods. So we started to develop, and after that we discovered other connections with red people. And one of them that I'm going to describe is a sensitivity to aluminium. So they had a metal that they had a strong affinity or an inability to detoxify. So we started to build a pattern that red people, in this case, were medium height, they were sensitive to wheat and highly sensitive to exposure to aluminium and so on. So we started to develop a little bit of a program. And it's those programs that I want to share with you and look at each of the three body types. So first of all, we'll do stereotypes, the true person. And then what we'll do is we'll look at people who are a bit of a mix of between one body type and another. And I think it's correct that you should be one body type. You're better, you operate better because of the relationship of the body type to the various endocrine glands. Now, about 8-10 years ago, I was asked by the kinesiology group to give a talk on body types. And when I started researching this with the endomorphs and ectomorphs and mesomorphs, most authorities on this, when I studied into it, said that most people are blends. You know, most people are predominantly, let's say, a mesomorph with a touch of endomorph in them, and so on. So they were blends of it. And I thought, well, am I talking about three body types as three pure body types? So I thought, how could I tell if I got a patient who weakened to green and didn't weaken to red and didn't weaken to blue, that they might have a touch of one of the other body types in them? And so I thought, let's test it against both eyes. So what we did is we put the acetate across both eyes, let's say in this case the green, and the patient weakened. So a strong muscle weakened, indicating there was over-cone stimulation. Okay? And then what I did is I put the cone on one eye, and they weakened. But in some cases, when I put the same cone color on the other eye, they didn't weaken. But another color did. So we call these hybrids. Okay? So this particular hypothetical situation would be, I would have called a green dominant with a touch or less dominant red or blue aspect in the other eye. So that was my mix, and I thought, this is fantastic. You know, so we could design a lot of acetates of these mixed colors. So we would test people with a red one on this eye and a green one on this one and so on. And that was quite interesting. And then we started to develop the idea that maybe people weren't always consistently one color, that they swapped between those two. They didn't usually become another color, but they would swap. And Jill was a very good example of this, wasn't it? You were predominantly a green-blue when we met sort of 3.5 or so years ago. And the dominant one was which color? Green. Was green. So on green days, she was a bundle of laughs. But I did notice sometimes she weakened on a blue day. Okay, and so green days meant she weakened to green predominantly, but the other eye, which probably was the left eye, let's say, weakened to blue, but not in the clear. In other words, you put the blue acetate against both eyes, she didn't weaken, but only on the one eye. Okay. Now, what we noticed is when she got an infection at all, she would weaken to blue and not to green. So there was a little bit of changing of what's going on in there. So in other words, the expression of these genes was altering according to the demand. That sounds like epigenetics, doesn't it? And of course, when we gave her the right remedy, she went back to the constitutional colours that she was to begin with. Now, green people have particular good things and bad things, all right? The green people have certain foods that they're sensitive to, and certain things that they're not sensitive to. So there's good and bad to every body type. And we know that there's certain heights. And one of the things about Jill is she is more of a red. She's got long, thin fingers. She loves meat. Okay, so she's a carnivore. Okay, this is a key bit. And she loves wine. Okay, and wine has no problem for her whatsoever. Okay, now there's a body type which doesn't get on well with alcohol, and that's a blue. Okay, but she's half an inch shorter than the average red. Okay, only by half an inch. Okay, so on good days we can stretch her. But red was not a colour she weakened to. Okay, she weakened to blue, which was in, her height is in the blue zone, but her body build is exactly a red, which was she wasn't weakening to, but she was half an inch out. Okay, so we thought we could call her body type if I looked at her from the structure and said you're actually a short red. This could be a detrimental or derogatory statement. You're a short red. But what we found is on myself, when I first started doing this 15, 20 years ago, I was a red. And I weakened to the red acetate. Then when I got into looking at the two, I was a red-green. So I was red on one eye and green on the other. But I never weakened to the green acetate as such. Although I had some tendencies towards a green, and because I always got a rash on my tummy if the buckle on my jeans, the button on my jeans, touched my skin on a sweaty day. If I was gardening or something like that, I'd always get a bit of a rash. And that rash or nickel allergy is typical of green people. They have problems with nickel, as we'll see. So I knew I got a little bit of this going on somewhere in there. But again, I wasn't a middle height and certainly not on the thinner side. So I was more body-wise, if you looked at me, you'd say, well, you're a green, much more than that on that. And what we discovered, and we're going to show you and share with this, is that emotions play a big role in our metabolism and our body gene expression. So I mentioned that when you're under stress, you don't get taller or shorter, but you can get wider or thinner. So something happens to your hormones when you're under stress. And this action occurs through the cascade of hormones from the hypothalamus to the pituitary to the thyroid, adrenals, and gonads. And those three hormones, or three glands, rather, the thyroid, the adrenals, and the gonads, are the principal coordinating glands in the body. And we found eventually that, of course, this is where the link was, is that people have their principal coordinating gland in their body type. So as we look at each body type, the red, green, and blue, or however you want to define those, ectomorphs, mesomorphs, and so on, is there's a gland which is the predominant gland. And that's what organizes their metabolism, but at the same time organizes also everything that goes wrong with the person. Okay, so if you've got a red person, for instance, which we're going to talk about first, whose dominated or prime coordinating gland is the thyroid gland, that person is, everything's going to be related to the thyroid. Okay, so when they gain weight, they'll gain weight in a hypothyroid way. So they would normally be on the leaner side because they have a faster metabolic rate and they love their meat. They are meat-eating engines. Okay, so we have a big problem here when we have a person who is red, and a typical red body, and they're a vegetarian. Because that's not the full fuel that they should be eating, and you can 100% say this person is going to be deficient in vitamin B12 because they're not getting B12 in, because there's no source of B12. Whatever anybody tells you, as far as cheese and eggs, forget. It doesn't. Never muscle tests. Fish doesn't muscle test. It has to be meat, and ideally it has to be red meat to get the B12 into a person. So they end up having to supplement it. So you're guaranteed that a red person will have this. But there's lots and lots of things about a red person which we want to get into now. So I'm going to come back to what happens if a person doesn't weaken to a colour, or occasionally we find people actually weaken to black. in other words, a deficiency or absence of a colour. And we're going to look at dim vision problems with the rods. But we want to concentrate for the next 3 chapters as such, each one on each body type. And these are related to the cones. So at this stage, we're just going to call them red, green, and blue body types. And remember that the red, green, and blue refer to the colour that the person weakens to, because this colour overpowers their cones. Okay.